Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. This video begins our exploration of grammars, and we're going to look specifically at regular expressions and combinatorial parsers in Scala. But to really understand those concepts, we need to introduce grammars, and in particular the Chomsky grammars. The idea of a grammar is a formal way of representing kind of text transformations, strings, and how you can express formal languages. In the textbook, in the first half of the textbook, if you have the book, some of the example projects used what is personally my favorite type of grammar, which are called L systems. We're not going to deal with L systems here. We're going to look at the Chomsky hierarchy because it is relevant to the tools that we're talking about. So let's first talk about what a grammar is. Formally, a Chomsky grammar is represented by a few things. We have a set of what is the alphabet, and that alphabet is generally broken into two types. What are called non-terminal values, as well as the terminal values. And as you can see from the way I'm typing this, it is characteristic to represent non-terminals as uppercase letters and terminals as lowercase letters. It is also typical to always include a special value in there called the start symbol. So when we build a string using our grammar, we start off with just a single symbol of our start symbol, and we let it evolve over time according to a number of productions. Productions are of various forms, and we'll talk about that for each of the different types of grammars in the Chomsky hierarchy. But in their simplest form, they have something on the right, so for example, our start symbol, and then some other string on the left, which could be composed of both non-terminals and terminals, depending upon what we are doing. And we are done generating a string when all of the characters are terminals. So typically what's over here is going to be a non-terminal because the non-terminals turn into things. This varies a little bit depending upon exactly what level in the Chomsky hierarchy we're at. So to give an example of this, we'll start off with a simple example, and I am going to let's go with A, and then A becomes either A or AA. Okay, so this is a simple example of a grammar. Our start symbol can turn into a capital A, the non-terminal A, and a non-terminal A can either become a lowercase a or an uppercase a. We use the pipe here to represent or. It is also possible to write this out in a longer format like this, but I will go with this notation. Not only does it save me typing, but it will work well with something that we're going to look at here in a bit. So, what happens with this particular grammar? Well, we start off with our start symbol, and the way that you evolve Chomsky grammars is you can pick any non-terminal in here and apply any rule that's over here. Well, in this case, the only production that we have that involves the S turns it into an A. So the second step in our moving the string forward has to be an A. At this point, we have a choice. So we could turn it into just a lowercase a. That would be taking the production that produces this, in which case we're done, because we have a string that has only a single a single terminal value in it. Alternately, if we take the other path, we get AA. If we were to take I didn't want that. If we were to take that path, really, I hate when tools decide they're smarter than you. If we take this path, well, we have one letter A here, so we have to apply a rule, and we can either get AA or we could get AAA, depending upon which one we pick. If we picked AA, we'd be done. If we pick AAA, this proceeds further. You can hopefully notice at this point a trend. This grammar right here represents it represents the language of one or more A's. And so any string that includes one or more A's I can generate with this grammar. So back to the Chomsky hierarchy. This grammar is a member of the simplest set of Chomsky grammars called the regular grammars. And so in the regular grammars, the rules need to have the form either of a non-terminal goes to a terminal. I guess technically I broke the simplest rule for this, or a non-terminal goes to a terminal followed by a non-terminal. And note that this can be simplified if I wanted here to make this so it truly fits the values for the regular grammars by doing that. In fact, that option there is exactly what we'd have. I could change this to a B because I can have multiple terminals as well as non-terminals, kind of as many as you want. Normally we're writing this in a simple alphabet though, so there are single characters and that limits how many options we have. Regular grammars are somewhat limited. This simplicity in what we're allowed to specify for their rules means that they can't do all that much for us. The next step up are what are called context-free grammars, and context-free grammars allow you to have the form of any non-terminal goes to, I'll put a question mark, whatever we want here. How about doing italics for, what's a good, there. Where the italicized Z can be any combination of terminals and non-terminals. So basically I can take any string that I can generate from my alphabet, and it's allowed to go on the right-hand side of a context-free production. The next step up is context-sensitive. Context-sensitive has the, I'll put another Z, A with an italicized Y there. Once again, dealing with a tool that thinks it knows what I want to type. And this has to become, the Z can stay the same, except I can replace now the A with any combination of terminals and non-terminals over here, and then that same Y that we had before. So the difference between context-free and context-sensitive, in context-free I can replace my non-terminal with anything that I want. I can do the same thing in a context-sensitive. The difference is, in context-free, what's around the A doesn't matter, and in context-sensitive it does. So it is context-sensitive. Where it appears in the string and what's around it are significant in this case. Okay. The last class of grammars for the Chomsky hierarchy is the recursively enumerable. No, that's not spelled right. There we go. And there are no limitations on this. You can have anything become anything. So I guess I could write this using the notation that I'm doing. Z becomes Y, where those are lowercase italicized, so this is any set of terminals and non-terminals becomes any set of terminals and non-terminals. Each level in the Chomsky hierarchy is actually nicely represented by a particular simple machine. Simple, I guess, with complexity growing. Down here in the regular grammars, these are represented by what's called a finite state automata. Context-frees are push-down automata. these finite state machines, these finite state automata, have no memory, and that is one of the things that's lacking in what you can actually do with regular expressions. Once you go to context-free, you have a push-down. That term push should invoke in your mind the idea of a stack, and indeed it has a stack as its memory. The context-sensitive is a linear bounded Turing machine. I know I'm not getting that quite correct. I don't have my notes up here in front of me. Significantly more complex device. But the interesting thing about recursively enumerable is that it is equivalent to a Turing machine, which means that theoretically you could write any program, solve any problem you want using grammars of this style. It is a complete model of computation, and you can use it to solve any problem. So instead of programming in Scala, you could decide that you're going to program in recursively enumerable grammars. This is not a recommended path. Whereas Scala was designed to help you solve problems, while these are powerful enough to do this, they aren't. So what we're going to do in the next video is I'm going to come back. We're going to use a little tool that I've written to look at some grammars and see how they evolve, and then we'll actually talk about the case of the regular and context-free and how we can use them in Scala.